In this episode, we're going to talk about electromagnetic waves, how they travel, how they're produced, what happens when they meet a reflecting surface or when they're incident upon two different media. Well, all this is very, very important, but there's a problem. All electromagnetic waves come out of Maxwell's equations. Maxwell discovered this about 250 years ago. Now, the problem is that not everyone has studied Maxwell's equations. And so, ideally you should have, but let's admit that not everyone has. Nevertheless, we can still proceed because in physics, you learn things step by step, incrementally. And so you can learn about Maxwell's equations later. For now, we will return to the wave equation, what you saw with the string earlier, then with sound waves, and then we will make our way up from that. Our discussion of electromagnetic waves should have as its starting point Maxwell's equations. That's around 1860 or so. But as I said, we're not going to go into Maxwell's equations. However, from those equations, you get the following wave equation. And this is a wave equation that will be for the electric field. And I'm going to be talking about a wave that's moving, let's say, in this direction, which we shall call the x direction. Now, from Maxwell's equations, you can prove that the electric field will be perpendicular to the direction of travel. So the wave is going like this, and perpendicular to this is the y direction. And in the y direction is the electric field EY. And that electric field obeys the wave equation, d2e dx squared minus 1 over c squared d2 dt squared ey equals 0. So this is for a wave that's been somehow emitted, is traveling along the x direction, and the electric field is perpendicular to that. So if you were to place a charge, that charge would want to go up and down as the electric field changes with time. I'll come to the magnetic field in just a little while. Okay, so now you know very well how to solve this equation. That solution is, you've seen it many times, is just any function of x minus ct. And now c, of course, is the velocity of light. In particular, we could have cosine solutions. We could have, so for example, Ey could be some constant, and now I'll need to call that constant something. So let me call that Ey 0 maybe, sine of kx minus omega t, where we know that omega has to equal to ck. That's what you learned is called the dispersion relation. So the ratio of omega to k is the speed of light. This here is the amplitude. It's the amplitude of the electric field in the y direction, and the y direction is the perpendicular direction to the x direction, which is the direction of travel. So it could be this, it could be cosine of kx minus omega t, etc. Now, it could also be the case that the electric field doesn't point in the y direction, it could point in the z direction, in which case Ez would be a function of x and t, which is the amplitude Ez and either sine or cosine of omega t, actually both of them. And this would be the amplitude for the electric field in the z direction. Now that's for the electric field. Now from Maxwell's equations, again, so this is the wave equation for the electric field. There's the wave equation for the magnetic field. So in the first case, when the electric field is in the y direction, then the magnetic field is in the direction which is perpendicular to both the x and the y directions. In other words, it is in the z direction. And d2 dBz, x squared minus this, that's equal to 0. Now, this is the wave equation for the magnetic field. The magnetic field is perpendicular to the direction of travel to the electric field as well. And the solution, of course, would be that Bz would be equal to, well, we'll have to give this some other name, but okay, so let me call that for now Bz0 sine of kx minus omega t. Now, from Maxwell's equations, you can actually show that this must be equal to that. So now I'll come to units. So in CGS units, that is to say centimeter, grams, second units, we have that Bz0 is just equal to EY0. Whereas in meter, kilogram, second units, MKS units, it's only slightly different. It's that Bz0 is EY0 divided by the speed of light, c. Okay, now this was the equation for the magnetic field when the electric field is this. What about when the electric field is in the z direction? Well, in that case, the magnetic field will be in the y direction. Now, this can be a little confusing, but let me draw it again over here. So if the electric field is like this, the magnetic field is perpendicular to it and is like this. So this is EY, this is BZ. On the other hand, if you have a wave that has the electric field in the Z direction, so if I talk about this, then the magnetic field will be in this direction. So this will then be the magnetic field and this will be the electric field. This is what is called Y polarization. So the polarization is the direction of the electric field. So in this case, this being the x direction, the electric field is in the y direction. In this case, the electric field is in the z direction, and guess what? We're going to call this a z polarization. Here is an electromagnetic field, just as discussed, which is traveling in the x direction. Its speed is v, and presently it is polarized in the y direction. So let me move this around a little bit so that you can see. You see that the electric field lies in the y direction. Okay, so now what I can do is, from the options provided here, I can now set the electric field in the y direction equal to 0, and instead the electric field in the z direction now will be this. Here you can see that this is also a wave that's moving with speed c in the x direction. And if I move the wave here, you can see that the electric field is completely in the z direction. Now let's go back to the y-polarized wave and now look for the B field as well. So, as explained earlier, again, you have a wave that's moving in the x direction. The electric and the magnetic fields are traveling perpendicular to each other. You see that the magnetic field, which has been colored blue, is perpendicular. So let me take this perspective over here. You can see that these are exactly perpendicular to each other. And now, what happens if I go to the other case, that is to say, the wave is polarized in the z direction? Well, then the magnetic field is polarized in the y direction. Now, of course, I can have a mixture. So now let me turn off the magnetic field. Here is now pure y polarization. I'm now going to take a wave that has half its amplitude in the y direction and half in the z direction. So look at this. Now, this wave has its electric field tilted. So let me move the axis like this. You see that it's at 45 degrees with respect to the ZY axis. So this has a direction of polarization. We will call this polarization that is at 45 degrees. In other words, this angle here is 45. Now, suppose I was to make the y component less and less and less. Well, it would be polarized entirely along the z direction. If I was to make the z component less and less and less, it would be polarized entirely in the y direction. And what about the magnetic field? Okay, so if I look at the magnetic field, it always has to be perpendicular to the electric field, no matter which direction the electric field is pointing in, and both of them have to be perpendicular to the direction of travel. And now you can see that if I change the electric field polarization, its relative strength there, then the magnetic field simply follows it. So here is the wave. Let me give another perspective here. So here is the wave, which is polarized at 45 degrees. The magnetic field, which is blue, and the electric field, which is red, are still perpendicular to each other. Let's now discuss polarization in a little more detail. So the polarization, you remember, is just the electric field's direction. But then anything that has direction can be represented as a vector. So the electric field is actually a vector. It's got components EY and EZ. And so if the wave is traveling like this, then that vector will be pointing in some direction which is perpendicular. So it's either here or here, perpendicular. In other words, if we draw the y and the z directions like this, then the electric field is a vector like this. And so let's call it vector E with components Ey and Ez. Now, E can be written, therefore, as E sine of kx minus omega t or cosine of kx minus omega t. And this is what is called the polarization vector. Now, both polarizations, Ex and Ey, can travel equally easily in free space. But then, what if you have a material that can pick out one direction of the electric field, and that is what is called a polarizer. So, this picks out one component of the electric field. So either the y component or the z component, it will allow to go through. Think of it this way, that suppose I have a slit like this. So this is a narrow slit. Well, the wave that is polarized along will be able to get through, but the wave that is polarized sideways like this will be blocked by this polarizer. This is the principle of Polaroid glasses. Now, Polaroid glasses help you avoid the glare when you look into bright sunlight. And of course, they have many, many other uses as well. You can think of a polarizer as follows. If I have a polarizer, it's really something with a direction. So if there's this polarizer, I can twist it around. And this polarizer then can act upon an electric field. And it gives, well, P dot epsilon sine of kx minus omega t. In other words, the amplitude of the electric field that comes out is determined by P dot epsilon. So if I make the polarizer perpendicular to the polarization vector epsilon, then no amplitude will come out. So there'll be no electric field coming out. But if it is along the direction of the electric field, then all of it will come out. Here's an illustration of what I just told you. So imagine that you're looking through an eye hole at polarized light that is coming towards you. Now, you have a polarizer which you can rotate. And I'm going to rotate this now. So I've rotated it by a small amount. You still don't see anything. But now let me rotate it. And you're seeing a cat or a dog over there. And now if I rotate it more and more, all the electric field is coming through. And so when I rotate completely in the direction of the electric field, then all the light comes through and the image is bright. Now suppose that I rotate back to halfway in between, that is to say to 45 degrees. So let me get here. Now 1 over square root 2, that is to say epsilon dot p, which is cosine of theta, is 1 over square root 2. And so 1 over square root 2 of the intensity of the electric field is getting through, which means that half the power is getting through only. So if I move it all the way here, I get 0 power that is coming through. The electromagnetic wave that is reaching you carries 0 power. And if I move it all the way here to theta equal to 0, back again, then you're getting all the power that is in the electromagnetic wave. Another quick look at the same phenomenon here. So here we have an electromagnetic wave polarized along this direction. And now I'm going to put a polarizer. That polarizer's direction P, the vector P, is along this. And now let me change the angle of the polarization, and you see that the wave that comes out gets less and less. If I change it more, it disappears. If I change it still more, it'll go back to the original value. And so this is how a polarizer works. It lets waves through that are polarized in one direction. It stops those which are polarized the other way. We've talked about how electromagnetic waves propagate. They go from one point to the other. But where are they produced? How are they produced? So now let's focus upon production of electromagnetic waves. Well, these waves come from acceleration of charges. So whenever there is a charge that is accelerating, you will have electromagnetic waves coming out. But although this follows from Maxwell's equations, let me give you a qualitative understanding of this. So suppose that this is a charge over here and this is another charge over here. You know Coulomb's law very well. That law says that the force between these two is just E1 into E2 over R squared into the unit vector that connects them, like this. That means that the force is entirely in the direction of the vector which connects the two charges. Now, this force comes because of an electric field, and obviously that electric field produced by E1 at E2, you will write therefore as E1 over R squared R hat. So the charge E2 simply experiences what is produced by E1, and that force is in this direction. Okay, now this was the static field. And it goes down very fast. It goes down as 1 over R squared. Now, you can show that for a moving charge, for an accelerated charge, in fact, that there is a component, E, which goes down as 1 over R. And this is what is called the radiation field. So instead of going down very, very rapidly as 1 over the square of the distance, this is going down as 1 over the distance. And this is really what accounts for the electric field that goes out from an accelerated charge. You can show a simple formula that holds for the production of power. So if P is the power that is radiated by an accelerated charge. So suppose there's this charge over here, let's call that E, and that charge accelerates. And its acceleration is in some direction with some magnitude. In other words, A is the acceleration of the charge. Then the radiated power is 2/3 the square of the charge over the speed of light squared into a dot a. So as I said, we're not going to prove this. This is something that comes out of a calculation, which we're not going to do. But note the following, and it's important to get the physics right. So first, the sign of E doesn't matter. In other words, if you have a positive charge or a negative charge that's accelerating, it doesn't matter. It's because the square is the same. Secondly, the sign of A doesn't matter either. In other words, if it is accelerating, well then A is a positive quantity, and if it's decelerating, it's a negative quantity, but here again the square is coming in. So all that is required is that the charge speed up or slow down. In both cases, it's going to radiate power, and that power you can measure in terms of ergs per second or joules per second. Let's understand this better with an animation. In this animation, we have a charge here. It's an electron in a wire that can move up and down. And far away is an antenna, and here there are also electrons that can be made to move up and down by an electric field, of course. Okay, now normally, if one just thinks of it in terms of Coulomb's law, the electron here communicates with the electron here only through the Coulomb force, and that is a 1 over r squared force. But if I wiggle this electron, then a wave travels out from here. Here you see the electron going up and down, accelerating. So it's accelerating power according to the formula that I just showed you. And it's producing an electric field that is moving outwards. Its amplitude is decreasing slowly. Slowly means 1 over r, not 1 over r squared. In other words, we are not in the static field, we are in the radiation field of this electron. The magnetic field is not shown over here, but from what you have just learned, it is, of course, also moving outwards in this direction, and it is perpendicular to the electric field. The electric field are these arrows which are going up and down. Waves produced by some source can move along until they meet some impediment. They could meet a reflector. So we're going to talk now about reflection of waves. Imagine that there is a smooth reflector. Now, that reflector, what exactly is it? Take a surface, a metal surface. Now, it's got a lot of electrons in it. Billions and billions of electrons that are free to move. So, an electromagnetic plane wave comes along, and I'm going to show this to you in an animation later. But when that wave comes along, that wave has got an electric field, and in that electric field, every electron is going to wiggle. Wiggle means change its speed, which means it's accelerating. And now you've just learned that an accelerating electron is going to radiate power. So basically, when a wave comes, it induces an acceleration among the charge carriers, and the motion of those charge carriers leads to an outgoing wave. And as you know very well, what will happen is that it will be reflected at the same angle that it was incident at. Here an electromagnetic wave is on its way towards a plane reflecting surface. It is at an angle of incidence of 30 degrees. Now watch what happens when it strikes the electrons or whatever is responsible for the secondary emissions. So you're getting waves being emitted outwards. This is Huygens principle at work, but with a physical reason. It's these free electrons which are going back and forth and they're radiating outwards. So again, this wave is coming in. It is shaking the electrons on the surface which are radiating, and you are seeing something quite interesting, that all these wave fronts are joining up together to give you a plane wave front like this. So the circular waves, watch where each circular wave has started from. So this circular wave started from here, from this electron, and then moved outwards and then joined up with the other circular waves produced by all the other radiating electrons, and so you got a plane wave that's now headed outwards. Look at the angle of incidence versus the angle of reflection. As you well know, these two are exactly equal. But why are they equal in this picture? Just watch. Now here, what you can see is that the wave front, which was perpendicular to the incoming wave, to the incoming direction, now has radiated outwards. And now it's for you to figure out. It's very simple. Just take a piece of paper and you will see that the incoming wave and the outgoing wave must make the same angles with respect to this normal. I'll leave this as an exercise for you. We'll now try and understand what happens to electromagnetic waves that travel through a medium. Well, you know that if there is free space and there's a wave that's traveling along like this, then first of all, its frequency is related to its wave number through the speed of the wave, the speed of light, since we are talking of electromagnetic waves, and this is the speed of light in vacuum. Now, suppose it encounters a medium, and the medium begins somewhere over here, and then the wave will go straight through if it is a transparent medium. Now, we want to understand what happens to the electric and magnetic fields inside over here. And that can be done properly only through Maxwell's equations. But behind those equations is a physical idea. And now let me come to that physical idea. So inside this medium are electrons. Now, those electrons are bound electrons. So imagine that there's an electron over here, and that electron is bound to something, let's say the core of an atom, its nucleus. And this electron can then bounce up and down like this. So when this wave enters the medium, then this electron will be set into motion. Now, as this goes up and down like this, you've just learned that every accelerating electron radiates electromagnetic waves. And so out come electromagnetic waves. They will have the same frequency. So this omega and this omega will be the same. But now everything depends upon how strongly this electron is bound to the core of the atom or whatever. And so there is absolutely no requirement that the speed in the vacuum and the speed inside the material be the same. And so although omega will be equal to c times something, it'll be the speed into the wavelength in the medium. And so the dispersion relation has changed. Now the ratio of the frequency to the wave number is something else. It's not the speed of light in vacuum. This is the speed inside the material. And of course, the ratio of C to C prime will be different for different materials. We give this a name, mu, which is called the refractive index of the material. This is a number that's bigger than 1. So for water, it would be, I think, something like 1.5 or so. It would be different for glass, different for various other materials, and so forth. But this is the fact that this is bigger than 1 for glass means that the speed of light in glass is going to be less than the speed of light in vacuum. Now we shall try and understand what happens when light is incident. So let me take a wave front that is coming, hitting this. So there are two media over here. There's medium 1 and there's below that medium 2. Well, part of this is going to be reflected and go back. And of course, the angle of reflection and the angle of incidence are both equal to each other. But then part of this is going to go through. So some of this will emerge into the medium. And if we call this the angle theta, then this angle over here will in general not be equal to theta. It'll be something else. We shall call this the angle theta prime. And then it turns out, and then again this follows from Maxwell's equations. If you do this properly, then sine theta over sine theta prime turns out to be mu. And this is the famous Snell's law. Let's see how all this works out when we look at this in terms of Huygens principle and see how secondary radiations conspire to give you wavefronts that move out. Here comes a wave that comes along, and I've chosen the same angle of incidence, 30 degrees. Now you see that the secondary waves are being produced both in the first medium as well as in the second medium. And the second medium waves are moving slower because the second index of refraction has been chosen to be 2. In other words, mu is equal to 2. Here there's vacuum and mu is equal to 1, obviously. Now watch this again. And this time, focus your attention upon how the outgoing wavefronts are being formed below. So you see that there's a wavefront that's formed over here. Again, that wavefront is moving slower relative to the wavefront that's on top. That's because of the difference in the refractive indices. And soon, what you will have is the wavefront has moved out, and then effectively we go back to the situation with zero field on top and zero field at the bottom. One last thing which will help us improve our understanding of electromagnetic waves, and that is microwaves. Now, you all very well have used microwave ovens, and you've probably wondered how they work. Inside the oven here, microwaves are produced by a klystron, which is a device that produces electromagnetic waves of a particular frequency, the microwave frequency. Now, let's see exactly how that works. Let's begin with a single water molecule. So water here is 2 hydrogens and an oxygen, and this water molecule can rotate around freely. So when an electromagnetic wave, a microwave, comes and hits it, that is to say it's in an electromagnetic environment, then it starts getting agitated. Of course, it gets more agitated if I increase the amplitude like this, and less if I decrease that. Now, there is no such thing as the temperature of a single molecule. Heat and temperature, they are concepts when you have many, many molecules. So let's take a single line of molecules. I'll click on that over here. And you can see that these molecules are randomized. Their energy gets randomized. But that energy is coming from the electric field of the microwaves. Now, if we go to many molecules, you see that the electric field is increasing, decreasing, it's inducing a random behavior in the molecules. And so the temperature has gone up. This thermometer is indicating the average random kinetic energy of the molecules here. And where is it coming from? Obviously, it is coming from the microwaves, the electromagnetic field, and that energy is proportional to the square of the amplitude of the microwave field. So let's see now what happens when you have a cup of tea or coffee and you start pumping in microwaves from the microwave oven. So right now the temperature is around here, quite low. Once we turn on the power, then the microwaves start coming in and the random kinetic energy starts going up, and the temperature keeps going up and up. I'm sure Maxwell must be very amused to see this application of his equations.